Hey guys, this is Shankar from Doubly, and today we are going to look on what are linked lists. Before we move on to looking what are linked lists, we'll have to know how do we store a list. A list is a set of continuous objects which are stored at contiguous locations. So for example, an array can be a list. So as you can see here, we have A, B, C, D, E, F and G. So these are blocks of data which are stored at contiguous locations. But is there another way? Yes, there is. This is where linked lists come in. For an array, we have something called as an element. So for a linked list, it's something called as a node. So consider this white region to be a node. So it consists of two attributes. One is the data, which will hold the data value. It could be either an integer, a string, or a char, or boolean, etc. And the next is called, next. So this will hold a location for the next node in the sequence or the list. So before we go on, we'll see how the data is stored. So this is the image of a memory allocation space in the storage. So for example, consider we have four objects, A, B, C, and D. For an array, we said that these will be in continuous memory location. So for example, if A is in 99, B will be in 100, C will be 101, and D will be 102. But what if we have to store data which is at 103 continuously in the list? So this is where linked lists come in. Consider this image. Now here we have the four objects A, B, C, D along with their locations in the memory space. So this is how the whole structure works, the linked list structure works. So A's node, that is the next of A's node, will contain the location of B, that is 100. So this is what happens. We'll have 100. Similarly, B will have the next value to be as 101 and so on. But when we reach the end of a linked list, or if the number of objects in a linked list is determined, the final node will have its next value to be null, since there is no other linkage to be done. So this is what is the linked list structure. And always, a linked list structures, the first node of the linked list is always called as head. This will be useful in traversing the whole linked list for carrying out different operations such as insert, delete, search, get length, etc. These are the different linked list operations we'll be covering today. Insertion, deletion, display, length, and one special case, that is to get the middle term of a linked list. Before we move on to the different operations, we'll have to know coding a linked list structure, but how? For that, we'll have to look into the basics now. The basics cover classes, what are variables, what is an object, and what is a constructor. A class is a blueprint from which individual objects are created. For example, consider the class student. Each of us have a unique blueprint. So that is, we have our own variables such as a name, roll number, and we have different methods as in functions. That is, we study, we write, we run, we play, we do whatever we want. Each of those individual actions are called as methods. And here, each object is considered to be a student. So what is a constructor you say for an object? That is, each of us are initialized with our own roll number. We have assigned different tasks. We are given new methods as in what actions to be done. So this is how we can briefly explain what's our class, variables, object and constructors. But now in terms of a linked list. Consider a linked list to be a class. We already said each linked list will have a head pointer which points to the first node in the linked list. So the head itself is a node. So what is the blueprint of a node? Here we can see the class node. This is the blueprint for the node structure. It has two variables. One is int data. It can either be int or a string or a char or boolean value, anything you want. And the next is node. What is node next? Why is there a node inside the node class itself? This node next points to the next node in the linked list. So the next itself is a node structure. So that's why we have a node inside a node. And this last line you see here is called as a constructor. This is what we use to initialize the whole node. So we pass in the value, the integer or string value to be assigned to the data object. And inside the constructor, we assign the d value to data. And the next is, since we are not linking to anything else, we are just leaving it as null. And below this diagram, you can see there's a line, linked list, list, new linked list. This is the creation of the object list with the blueprint of linked list. Now we'll look into how to insert a node into a linked list. For example, insert a node with data E. There are two scenarios to be considered here. But before that, we have to do two steps. Whenever we add a new node to the linked list, we'll have to first create the node with the data value. That is, this is the line in the code. That is, node new node is equal to new node of the data value. And the next step is we'll have to initialize the next value of the node to be null. Now we'll look into the first scenario. For an empty linked list, that is, there is no head. So the head pointer is basically pointing to a null value. So if you can see this if condition over here, if this dot head, if the head of the linked list is equal to null, then we create a new head value with the new node's value. That is a node which is to be added. So now the linked list consists of the node E. Now we'll look into the second scenario. Given a linked list, we'll have to insert node with data E. As you can see here, we have 4 nodes in the linked list already. That is A, B, C, D, and D is the last node. Now look into the code. We have added another else condition. This is how it goes. We create a new node, that is the last node or a temp node, whichever you want to name it, and we'll make it point to the head of the linked list. Now we'll have to traverse the linked list, and this is the code for traversing. While last.next not equal to null, now since last is pointing to head, while the next value of the head value is not equal to null, we'll change last equal to last.next. Now last will be B. Similarly, in the next iteration it will be C, and the next iteration it will be D. But now since the value of D, the next value of D is null, it will come out of the while loop, and last.next, that is D's next value, will point to the new node, and this will be the final output of the linked list. As you can see, we have A, B, C, D, and E. Now we'll look into how to delete a node from a linked list. So given a linked list A, B, C, D, E, we'll have to delete node C. Here we'll have to keep track of two things, that is the previous node and the current node. So we'll have to pass it through a while loop. So the while loop conditions are while temp.next not equal to null and temp.data not equal to the given value. We'll keep traversing the array. So at the first iteration of the while loop, current will be pointing to node A and the previous will be null. And in the next iteration, we see it's not given target and the not next value not equal to null. So in the second iteration, we have the current one to be node B and the previous to be node A. And since both the conditions are not met yet, we'll go on to the next iteration. That is, now current will be pointing to node C and prev will be pointing to node B. But now as you can see, we have the target, that is the current.data equal to the given node C, that is the key. We'll have to delink it. So this is how it goes. After we come out of the while loop, this is the statement to be run. That is prev.next, that is b.next value will be pointing to the current.next value. Since the current node is C and that is the one to be deleted, we'll change the previous is next to point to the next of the current node or the target node. And finally we get the list A, B, D, and E, and we have successfully deleted node C. Now we look into the code of deleting a node. As I said, we'll keep track of two things, that is a current or temp node that is pointing to the head and the previous node which is initially null. So first we'll check if the head node itself is the target node, that is if temp not equal to null and temp.data equal to key. So if the condition is met, we'll make head equal to temp.next, that is basically null, and we'll just return the null value. Or if it's not pointing to the head and we have not reached the target node yet, so we'll have to check on two conditions in the while loop, that is while temp not equal to null and temp.data not equal to the given target value. So we'll make prev is equal to temp, so we'll keep track of the previous value and make the next value as the current value. So this is how it goes. And if the condition is met, that is temp.data equal to key, and if the temp value not equal to null, we'll return, else we'll just change the linking connection, that is make the previous dot next point to the target dot next value. So this is how the code works. Now we'll look into how to display the linked list. So given linked list A, B, C, D, E, we'll have to display it. So how does this go? As I said, we'll have to keep track of the head node, that is the head will be used to traverse the whole linked list. So in order to display the linked list, we'll have to traverse each of the node and print it out. So this is how the code goes. So we'll have to create a node current which points to the head node of the linked list. And if the current node, that is the head node, not equal to null, we can carry on with the next condition. Else if it is pointing to null, the linked list is basically empty. So we look into the else condition if it's not equal to null. So while current node not equal to null, we'll just return the data value of that particular node. So and print it. And we then make the current node point to the next value of the current node. That is, you look into how it works. Here, now the current node is the head value. Since it's not equal to null, we return the current node dot value. And since the next value is also not equal to null, we'll go on to the next value. So here we have B. And in the similar fashion, we have C, D, and E. And since we have finally reached the end of the linked list, that is the next value is pointing to null, we have the whole linked list displayed out, and the output is A, B, C, D, E. And now we all know the saying, two birds with one stone. And in similar fashion, the next code is also the same thing, but with a little modification. This is called as length of linked list. So basically we'll have to return the number of nodes in the given linked list. So on a similar fashion of the previous, that is the display linked list code, we have while current node not equal to null, and the one small modification is we increment the counter every time we hit a node. So the counter is called as length, and while current node not equal to null, so for each node we increment the length counter by 1 and make the current node point to the next of the current node. And finally, when the while loop finishes, we just return the length. So for the output of the previous linked list, the whole length is 5. Now we look into how to get the middle term of a given linked list. We'll be doing this using a special type of algorithm called two-pointer algorithms. Consider the given linked list A, B, C, D, E, and the final null node is just for reference. So keep that in mind. So how do you get the middle term of this linked list A, B, C, D, E? Before we start, and the previous operations, we have used something called as a current node, which will be assigned to the head node. So in a similar fashion, we'll initialize two nodes over here. One is the slow node and the fast node. Each of them point to the head node. So for getting the middle node, we'll have to traverse the whole linked list. So this is how the whole fashion goes. So the slow and the fast nodes point to the head node, and at start they are at the same point, that is head. In the next iteration, we make slow point to the next node, and fast, as you can see, it goes faster than the slow node. So as you guessed, it will be pointing to the next dot next value. So in the next iteration, this is the output. Slow will be pointing to head dot next, and fast will be pointing to head dot next value. And similarly, we now have slow pointing to C and fast pointing to E. As you can see, the while loop condition has been broken. Here we have E dot next value is equal to null. So that comes out of the loop, and we return the slow pointer's data value. Since slow pointer points to C, the output of this whole code is C. So this is how you get the middle value of any given linked list. Now we look into the code of getting the middle term. As I said, we'll have to initialize two nodes at the beginning. That is the slow pointer and the fast pointer. Each of them point to the head node at the beginning. So while the head node not equal to null, and while the fast pointer not equal to null, and the fast pointer dot next value also not equal to null, these are the two statements to be done. As I said, we have the slow pointer which is slow and the fast pointer which is fast. So the slow pointer will keep traversing by 1, and the fast pointer will be traversing by twice. That is 2 steps. So fast pointer is equal to fast pointer dot next value, and slow pointer is equal to slow pointer dot next. And finally, when we reach the end of the while loop, we'll have to return the slow pointer dot data, since it will be pointing to the middle value of the given linked list. This applies for linked lists of all sizes. So this is how the code goes. Now we look into the types of linked lists. Till now we have been working with only one type of linked list, that is called single linked list. That is, it just points to the next node in the given linked list. Now there are two different types more. That is doubly linked list, where each of the node has three attributes. That is the data value itself, and 2 pointers. That is the previous pointer which points to the previous node, and the next pointer as usual which points to the next node. And the third type of linked list is called a circular linked list. where there are two types of variables in the main linked list itself, that is a head node and the tail node. Here the tail node will always point back to the head node, as in a circular fashion. There is one extra special case which is called as doubly circular linked list, which is a combination of both doubly linked list and circular linked list. Now we look into how a doubly linked list structure looks. As we have seen in the singly linked list structure, there are three main things for a linked list. That is the node head variable, which points to the first node, and the class node, which consists of the variables that is in data and next value, and a constructor which initializes the node. But as you can see in this diagram, we have one extra change that is in the class node structure. We have that is the end data, node next, and one additional thing which is called as node prep. This points to the previous node in the linked list. So it is linked both ways, as in the next value and the previous value. So this is a whole class structure for a doubly linked list. Now we look into how to insert a node into a doubly linked list. Now for example, insert a node E after the node B. As you can see the linked list, doubly linked list here, A, B, C. Now what we have to do is we'll have to insert E between B and C. So these are the 5 steps we'll be considering. First, create the node with the data. So we'll assign the value E to the data value of a new node and make the previous and the next point to a null value. Next, make next of the new node as next of the previous node. So given a previous node, we'll have to make the next of a new node point to the next of the previous node. So as you can see in the diagram, we have done that first. Next, make next of the previous node as the new node. So the next of the previous node, that is B, will be pointing to the next new node, that is E. And now make previous node as the previous node of the new node. So now B will become the previous of the new node E. And finally, we'll have to change the previous of the new node's next node. That is the previous of the new node's next node. That is the next node will be C. And we'll have to make it point to the new node E. So these are the 5 steps we'll have to follow on doing this. And this is how the code goes. First, we are trying to insert a new node given the previous node. That is after it. So if the previous node is null, the given previous node cannot be null because we are trying to insert it after it. So as you can see, the 5 steps have been written over here. Create the new node, make the new node dot next equal to previous node dot next, make the previous dot next as the new node, and make the new node dot prev point to the prev node. And if new node dot next not equal to null, new node dot next dot prev is equal to the new node. That is change previous of new node's next node. This is how the whole code structure flows. Now given a doubly linked list, we'll see how to delete a node. So for example, the given doubly linked list is ABC. Now we'll have to delete node B. You can just interpret what is happening from this given diagram itself. We are removing the connections between A and B, and we are removing the connection between B and C, and we are directly changing those connections and connecting A and C back together. And finally, we return the whole linked list. So we have successfully deleted node B. Now we look into the code. So first we look into the base conditions. That is, if the head value of the doubly linked list is null, or the given target value is null. If so, just return. Or if the given target value is the head value of the given linked list, just change the head pointer to point to the next of the head, given head value. So if that is also not true, we'll go to the next if condition. That is, change next only if node's value is not the last node. That is, if the node's dot next value is not the last value, we'll just change it to node dot next dot prev is equal to node dot prev. And similarly, change prev only if the node's previous value is not the first node. So if the node previous value is not the first node, we make it as node.prev.next is equal to node.next. And finally, we return the whole linked list. So this is how the code worked for doubly linked list deletion. Till now, I have only covered singular linked list and doubly linked list. I have not touched circular linked list because it's basically simply a linked list with an extra modification. That is, a tail node, that is the last node, will point to the head node. So now, before we start implementing this linked list, we'll have to know what are those time complexities for each of those operations. And if you know that, the laws of time are yours. Now, we'll look into those tables. For a single linked list, insertion at the start, that is the beginning, is basically O of 1. Because we are just inserting the new node, and making the head value point to the new node, and the new node next is rest of the list. And similarly for deletion, it's O of 1. For insertion at the end of the list or anywhere in between, it's O of n, because we'll have to iterate the nodes till we reach the target node, and then we'll have to insert or delete it. So it's basically O of n. And similarly for a doubly linked list, it's O of 1 and O of n at start and end. And deletion is O of 1 and O of n. For anywhere other than the start and end, it's O of n for everything. That is insertion for singly linked list and doubly linked list, deletion for single linked list and doubly linked list, and searching or traversing is always O of n. For example, we'll have to search for the third node. So we'll have to iterate 3 times until we reach the target node. So for both the linked lists, it's O of n. But why though? Why is it O of n? Now for example, consider this linked list with 4 nodes. Now I'll have to search for node number 3. So we'll have to iterate thrice. That is 1, 2, 3. So it's O of n. So we have reached the conclusion of our video, and till now we have only covered single linked list and especially doubly linked list. Why I did that was, we'll be implementing stacks and queues using doubly linked list, which we'll cover in a future video. And for example, some of the concepts, that is the doubly linked list mostly, would not have been clear for you all. So you can hit me up on Discord and post your queries on linked list, and I'll be glad to answer them. So this is Shankar signing off.